section we're going to talk about today is redox chemistry. So the word redox is a combination of the words reduction and oxidation. And so last time we talked about acid-base reactions. Acid-base reactions and redox reactions are probably the most two common types of reactions. So if you have an acid-base reaction, that's not a redox. So they're different. But they have some similarities. One similarity is that in an acid-base reaction, you can't have the reaction take place unless you have both the acid and the base present. You need both, right? Because, as we said last time, the acid has an H plus attached to it, sharing electrons through a somewhat weakened bond, so the H plus could be grabbed away from those electrons, and you need the base to grab it. You need the base to have a pair of electrons to come in. There needs to be a collision. The base is going to use its electrons to grab the H plus from the acid, and then that is an H plus transfer, right? You need to transfer an H plus, you need something to donate it and something to accept it. You need an acid and you need a base. In a redox reaction, we have a similar theme because we need two substances. Instead of transferring an H plus, like in an acid-base reaction, in a redox reaction, we transfer electrons. So in the most basic sense, we have something that has loosely held electrons relative to something else that could pick those electrons up. So again, we also still need a collision. The two particles need to come together and collide. And the one that has the loosely held outer electrons, the other one will have to collide, and its nucleus will have to attract those electrons and pull them away. So it's a very similar process. The collision exchange allows for the exchange of something between two particles that are involved in the collision. It's just what is being exchanged. If it's an H plus, it's an acid-base reaction. If it's a pair of electrons or a single electron or some number of electrons, it's a redox reaction. So to understand a redox reaction, some people use the mnemonic oil rig, and that can be a useful way to remember it. This mnemonic stands for oxidation is a loss of electrons, and the other part stands for reduction is a gain of electrons. So that's one way you can remember it from the point of view of what's happening with the electrons. That's perfectly reasonable. So when two substances come together, if it is a redox reaction, the one substance should be picking up electrons from the other. So the one that grabs the electrons, the one that gains the electrons, is the one that's being reduced. That's fine if you want to think about it that way. There are some reactions, though, that it will not be very apparent to you which atom is gaining electrons and which atom is losing electrons. So it might be difficult to tell whether which substance is being reduced and which substance is being oxidized, or which substance is undergoing oxidation and which is undergoing reduction. So another way to think about it is to say that a reduction, which the word reduction means to reduce or decrease something, is a decrease in charge. That's another way you can think about what a reduction is. So if something is going down in charge, either it's decreasing the quantity of positive charge it has, or maybe it's going from a positive charge to zero, or from zero to negative. If the charge is going down, becoming less positive or more negative, that's a reduction. And an oxidation is the opposite. It's an increase in charge. So if it goes from 0 to positive, or negative to positive, or negative to 0, or positive to more positive, that's an oxidation. So here we have an example reaction. We have zinc and copper. The zinc starts with 0 charge, no charge shown, so we assume it's 0. The copper has a +2 charge. And if we look at what becomes of the zinc and the copper after they react, we can tell what's happening with electrons. So if the zinc goes from 0 to then on the product side having a +2, what happened to it? Well, there's two ways to think about it. You can think about it going from 0 charge to increasing the charge, so that means it's an oxidation. You can also think of it in terms of what had to have happened to its electrons to do that. So if it started with a charge of 0, it had to balance the number of protons and electrons. And then to become +2, it had to lose 2 electrons. So the loss of electrons is also a way to think about oxidation. So I can identify that this is an oxidation process. Right? But the electrons are not just going to leave the zinc unless they have somewhere else to go. Right? They're still attracted to the zinc's nucleus when they're in that zinc atom to some extent. So if they're going to leave, something else has to attract them more. So it's the copper. Right? The copper goes from a +2 to a 0. So it's picking up those 2 electrons from the zinc. And so if we observe this reaction happening, not only can we tell that there's electrons transferred, we can classify it as a redox reaction, we can determine that the zinc is oxidized and the copper is reduced, but it also allows us to understand something about the behavior of zinc, its properties chemically, and the behavior and properties of copper. Because if the copper has the ability to pull electrons off of the zinc, that must mean that the copper's nucleus attracts those electrons better than the zinc. So we can start to look at substances and their ability to attract electrons or lose electrons. What area of your life is this probably most relevant to? Electricity. Yeah, right. Batteries. Right? So what is a battery? A battery is a thing that has a positive end and a negative end. Right? When you put your battery in your phone, it lines up the electrodes, the positive and negative end, or whatever other device you use the battery for. And so what this battery has is the potential to have electrons flow out of the negative end. Since electrons are negative, that's why they're flowing out of the negative end. They flow out of the negative end through your device and over to the positive end. And so there's a barrier inside the battery. Different batteries are designed differently, but there's got to be a barrier here. And what we have is electrons on this side. Maybe they're associated with a zinc or something, right? A neutral zinc, which has the possibility of losing 2 electrons. Maybe on the other side, we've got some copper +2 or something that can pick up electrons. So if there's a barrier and the electrons can't get through that barrier, but this reaction demonstrates to me, because it goes forward, that the copper is good at picking up electrons, and if I put copper 2+ and zinc together and let them just mix together, what I will observe in the end is that the copper will pick up a bunch of electrons from the zinc and become neutral. The copper +2 will pick those electrons up, become neutral, and the zinc will lose those electrons. So I know there's a natural better attraction for the electrons that the copper has than the zinc has. And if that's true, I can make a battery and take advantage of that, and that's something you would do in general chemistry too, to take that class. So your battery might involve taking copper, it might involve different elements. Lithium is a popular element for batteries. If you look at lithium, what type of properties does lithium have that makes it suitable? Well, it's a very loosely held one outer electron, right? Because lithium, if it loses that one electron, it will have the same number of electrons as a noble gas. So if I put lithium on my battery, I want it on this side with the negative. Because it has this loosely held electron that could be better attracted to another element. Another advantage of lithium is that it only has a mass of 6.9 on average AMU per atom, or grams per mole. It's a very lightweight element, so you can make a lightweight battery and you don't have it weighing down your device so much. But whatever substance you put on the negative side, it has to have some electrons that it attracts very loosely and not very strong. Then when you connect the wire or connect it to your device, the electrons flow out of there because they're more attracted to the other side of the battery. the positive charge on the other side of the battery attracts electrons, pulls them in, and that pulls the battery, the electrons through the device from the other side, and they move to the other side. Right, so this redox reaction, electrochemical reactions are really important for the way our society works. So we already mentioned that. So what's happening here? The zinc is being oxidized. As we said, we can think of that as a loss of electrons, or we can think of it as an increase in the quantity of positive charge. Either way, you can think about it that way. That means that the zinc is a reducing agent. Okay, so you also want to make sure you get straight what the term agent means. A reducing agent is not something that is reduced. Right? The reducing agent is something that's causing something else to be reduced. Right? That's what an agent is. Right? So it's not being affected itself, it's causing the effect on something else. Right? So as a reducing agent, the zinc, we recognize it as a reducing agent because the zinc is causing the reduction of the copper. Right? They work hand in hand. The zinc can't be oxidized unless the copper is reduced. And so the zinc is responsible for reducing the copper. That makes the zinc the reducing agent. And that the copper obviously then is oxidized. I'm sorry, the copper is reduced. Its charge is going from +2 to 0. It's a reduction in its positive charge. So that is reduced, and that makes it the oxidizing agent because it is oxidizing the zinc, or it's what is taking the electrons from the zinc, causing the zinc to lose its electrons, causing the zinc's positive charge to go up, causing the zinc to be oxidized. So if you have a reaction, you should be able to identify which substance is oxidized, which substance is reduced, which is the oxidizing agent, which is the reducing agent, where what is actually happening with the electrons and how they get transferred from one substance to another. So here's just kind of a visual depiction of what's happening there. So in this example, I've got this container, I've got a zinc, strip of zinc metal, and I've got in solution copper ion. Okay, so copper ions are notorious for being blue colored. Oops. The ions are in solution. Ions are usually fairly easy to dissolve because the copper ion will attract, if water is my solvent, the partial negative of the water through an ion dipole attraction that we talked about before. And water molecules will surround that ion with their partial negative, so I get to form a few nice, decently strong ion dipole attractions that keeps the copper dissolved in solution. So the copper ions get surrounded by water, they're moving around. If the copper ions I don't know why they have them colored orange here, they should color them blue because that's what's responsible for the blue color, but if the copper ions come in and collide with the surface of the zinc, that's where the electrons are located. So on the surface of that zinc strip of metal, there's this loosely held outer electrons, right? When we talk about metals, solids, metallic solids, what we said is the metallic solids have their nuclei aligned in a crystalline three-dimensional arrangement. Then there's like soupy electrons that flow over the surface of that because metals don't have very strongly held outer electrons. They're moving around, they have the ability to flow. And so that's what makes metals conductive of electricity, because if I have electrons here and they can flow anywhere over here, then I have charged particles that can flow over the surface or through the metal. That is what electricity is, flowing charge. So when a positively charged copper comes in here and collides, it grabs those two electrons because its positive charge attracts two of the soupy electrons on the outside of the zinc. And that forms a deposited layer of copper atoms, because once the copper, which was positive, picks up two electrons, it's not positive anymore. And if it doesn't have a charge, its attraction to water molecules is not going to be very strong. So the water molecules won't really surround the neutral metal atom. And so the neutral metal atoms stick to the other metal atoms on the surface of the metal. and they engage in having those soupy electrons flow over them and keep them connected to one another. But also when the copper grabs the electrons from the zinc, it doesn't have electrons anymore. It loses 2 electrons. So now when the zinc becomes charged, it moves into the solution. So now that the zinc has a positive charge, the water molecules with their partial negative will surround that and keep it in solution. So this is also a way of doing like electroplating. If you have a cheap metal and you want to plate it with gold or copper or whatever, you can put ions of the metal you want to end up plating the surface, and then you can have those ions accept electrons and form neutral metal atoms, and that would deposit a layer of those metal atoms on the surface. When we're analyzing redox reactions, we're often, it's helpful to break down the full reaction into half reactions. So what we mean by half reactions is the full process is a redox process. It involves both reduction and oxidation. Half of that is the reduction part, and half is the oxidation part. So if the oxidation in this case is occurring for the zinc, the oxidation half reaction would be just what's happening with the zinc. What is the oxidation part of that? Well, what's happening with the zinc is it goes from zinc 0 to zinc 2 plus. So if it's going to go from 0 to 2 plus, is it gaining electrons or losing electrons? It's losing 2 electrons. So those 2 electrons are produced. That's the oxidation part of what's happening. The zinc is losing 2 electrons. It's not like the electrons are just flying out, though, right? They're not flying out and going to the water or something. The copper has to grab them in order for them to leave. But if we just want to focus on what is happening with the zinc, it's losing 2 electrons. The 2 electrons are being produced. And then the reduction part of that is what's happening with the copper. So the reduction half reaction is that the copper picks those 2 electrons up. So in this particular example, the number of electrons that zinc has a tendency to lose is 2, and the number of electrons that copper has a tendency to pick up is 2. And since those are equal, my reaction is balanced, and I can write the full reaction as just the sum of the 2 half reactions. There will be other examples, which we will see, where if one half reaction produces more electrons than the other half reaction accepts, then I have to change the coefficients here to balance it. Right? So just like other reactions where we're balancing the number of elements on both sides of the arrow, in redox reactions we also have to make sure that the number of electrons are balanced on each side of the arrow. I can't have 3 electrons coming out and only accept 2 of them. Where did the other electron go? It has to be accepted. There has to be a full transfer. If any electrons lost have to be gained by the other substance. So in this case it works out because I'm losing 2 and then those 2 are picked up. Why is it that the zinc has a tendency to lose 2 electrons? Why not lose 1 or 3? Why 2? This is good. Most of you are looking at the periodic table. It's a good sign. So if we look at where zinc is as a neutral atom, it has an argon core, 2 electrons in the 4s, and 10 electrons in the 3d. So it has 2 valence electrons. It has the full 3d, the full 3s and 3p, but the 4s is the highest energy level that zinc has electrons in. There are 2 electrons in that 4s subshell, and so they're held out. They're the outer valence electrons. They could be lost, so that's why it loses 2. It could lose 1, but then it would still have 1 left in the 4s, and it's just not very close to the nucleus. There's a lot of shielding. So it loses 2. It has tendency to lose 2. And then the copper, if we start with the copper plus 2, since it has a plus 2 charge, it has the ability to pick up 2 electrons to balance out a charge. So that is how you look at half reactions. And then, as I forgot to mention, once the oxidation half reaction number of electrons produced is equal to the number of electrons accepted in the reduction half reaction, those cancel out. So just like math, anytime you have something equal on both sides of an equal sign, it can cancel itself out. And you don't have to show the electrons in the overall reaction because we recognize that they're equal in number. Questions so far? Okay, so let's say you had this reaction. Here you have hydrogen and fluorine producing HF. So here, if I want to draw what I'm dealing with, it might be helpful to have the Lewis structure to see what's happening with the electrons. I see that it's balanced, so that I have 2 total fluorine on both sides, 2 total hydrogen on both sides. Does this look like a redox reaction to you? Does it look like anything is losing or gaining electrons? Not really, because I don't have any charges. I mean, I don't have something going from a 0 charge to a plus charge where it's clearly losing electrons to create an imbalance in its charge. Everything is neutral. The hydrogen has 2 electrons here. Over here it has 2 electrons. So this is a redox reaction, though. Okay, so it gets a little bit more complicated. The first example we saw was really straightforward. When you can clearly see that something is changing its charge, you can clearly see that it's either picking up electrons or losing electrons. You know it's a redox reaction. So in this case, though, what we recognize is, we think about the hydrogen. When it's bonded with another hydrogen, the electrons that are shared should be shared evenly, right? Because both hydrogens sharing 2 electrons, they have the same electronegativity, they're pulling on the electrons with the same strength, and so the electrons get shared evenly between the 2 hydrogens. But if I put the hydrogen with a more electronegative atom, that other atom will attract the electrons more. So really we do have a change in the arrangement of the electrons around the hydrogen. Here the hydrogen has those 2 electrons shared well around it. They're shared evenly around it. It has more of an electron density around it because it's sharing those electrons more effectively. Here the electron density around the hydrogen is very minimal because the fluorine-hydrogen electronegativity difference is very large, and the electrons around the hydrogen are not going to be attracted very strongly to the hydrogen. So in this case, to determine that the oxidation and reduction has occurred, we can't just look at the charges because there's no charges. What we have to do is develop a system of creating oxidation numbers, which are similar to charges. They're just a little bit different. They allow us to classify reactions like this as redox reactions, even though there's no charges shown. They allow us to determine which substance is being oxidized, which substance is being reduced. And this is also valuable because it involves an exchange of electrons, and I could use this reaction also to run a battery if I wanted to as well. So we have to talk about oxidation numbers because you have to be able to recognize what the oxidation numbers are if you want to predict whether an oxidation is occurring or whether a reduction is occurring. So there's a couple ways to do oxidation numbers. I'm going to talk about the one I like most first, and then if you like that one, you can use it. If you like the other one, you can use it, or you can use both and make sure that they come with the same answer. So one way to find the oxidation number is to use a very similar method to what we use for calculating formal charge, which is why I like this method, because you should know how to calculate formal charge since we covered that a lot. And this method is similar. So as long as you apply the method we already talked about for formal charge and the slightly different method here for oxidation numbers, and you don't get them mixed up, then usually it should work out. So the method here is to start by drawing the Lewis structures. Then imagine that instead of sharing electrons, any bonded electrons are going to be pulled more toward the atom and owned by that atom if it's more electronegative. If the two atoms sharing the electrons are the same electronegativity, then they split the electrons evenly. Right? So once we draw the Lewis structures, then that's step one. Then step two, split the bonds. Either split the bonds evenly if the two atoms have the same electronegativity, or split the bonds unevenly if they have different electronegativities, then the one that's more electronegative gets both electrons that were shared. So in the case of the hydrogen, they have the same electronegativity, so when I split the bond, I give each hydrogen one electron. In the case of fluorine, they have the same electronegativity, so when I split the bond, they're going to split evenly and both pull the shared electrons one to each of them. In the case of the HF, they're not having the same electronegativity. The fluorine is more electronegative, so when I split that bond, I want to put both electrons on the more electronegative atom. Then calculate charges. And those charges will be equal to the oxidation number for that element. So what's the charge on a hydrogen if it has one electron? 0, right? It has one proton, one electron, keeps it balanced. So the oxidation number for this hydrogen is 0. What's the oxidation number for a fluorine with 7 electrons, 7 valence electrons? 0. Fluorine is in group 7A. It normally has 7 valence electrons to be neutral, so if it has 7, it's neutral. So its charge and oxidation number would be 0. On the right-hand side, the hydrogen now has no electrons. So if it has one proton and 0 electrons, that means it has one positive charge that isn't balanced. So I'll call that +1. That's its oxidation number. And the fluorine has 8 electrons, which means it has one more than it needs to be neutral. So that's a -1 oxidation number. So now I've got the oxidation number. That's method 1. Once you've got the oxidation numbers, then you can determine which substance is oxidized and which substance has been reduced. So which of my two elements is oxidized, the hydrogen or the fluorine? Here, oil rig kind of doesn't work so great. It works well in situations where I can see electrons being lost or gained, but here I can't really see that maybe as well. Maybe I can. I mean, I can see that the fluorine has kind of 8 electrons, whereas on this side maybe it looks like it has 7, so that's a gain of electrons. But I can definitely see, once I have the oxidation number, that for fluorine the oxidation number is going from 0 to -1. That's a decrease in the oxidation number. That's a reduction. And the hydrogen oxidation number is going from 0 to +1. That's an increase. That's an oxidation. So in this case, the hydrogen is undergoing oxidation. The fluorine is undergoing reduction. So when we say the oxidation number is the charge an atom would have if the electrons are transferred completely, that's what we're doing here. So really, in reality, we know that when HF forms, the electrons aren't transferred completely. And in these molecules, the bonds aren't broken, right? They're going to stick together to maintain their noble gas configuration. But to calculate the oxidation number, we just look at what would the charge be if the bonds did break, and the electrons were transferred either evenly or unevenly if there's an electronegativity difference. That allows us to calculate the oxidation numbers and see which substance is being oxidized and which substance is being reduced. So if we look at another example here, sticking with the same method, first thing we want to do is draw the structures. So good thing we have that skill from earlier in the semester. Then we want to break the bonds. Allow them to be transferred completely, either breaking them evenly, which is called homolytically, or unevenly, which is called heterolytically. So the nitrogens have the same electronegativity, so they'll split their electrons evenly. So do the hydrogens, they'll split their electrons evenly. But on the product side, the nitrogen's electronegativity is greater than hydrogen. So the nitrogen is going to grab all the electrons from all the hydrogens, and the hydrogens will be without them. So then on the left-hand side, I can calculate the nitrogen has 5 electrons. It needs 5 to be neutral, so it's neutral, 0 charge. Hydrogen is also neutral, 0 charge. It has the number of electrons it needs to balance out its protons. On the right-hand side, though, my hydrogens are all +1 because they don't have any electrons to balance out the positive charge in their nucleus. And the nitrogen here, the nitrogen, which normally needs 5 electrons to be balanced, but has 8 assigned to it, it's going to be a -3. So 5 minus 8, the oxidation number for the nitrogen is -3 here. So definitely in this case, again, hydrogen going from 0 to plus, that's an increase in its oxidation number. It's being oxidized. The nitrogen going from 0 to -3, a decrease in its oxidation number, so that's a reduction. Questions about that? Okay, so that's one method you can use. Another method, which the book focuses on a little bit more, is to memorize a bunch of rules. So these rules are on the formula sheet. If you don't want to memorize them and you just want to learn how to apply them, that's fine. You can use that method. One rule is that whatever the charge is on an atom, that has to be or a compound, that has to be the sum of the oxidation numbers. So what that breaks down to is, if I have an individual element, if it has a charge, that's also its oxidation number. If I have an individual element with no charge, that's also its oxidation number. So if the element is by itself and it's not bonded to anything, that's pretty straightforward. Whatever its charge is, that's its oxidation number. Because if it's not bonded to anything, we don't have to split up any electrons and change the number of electrons around it in any way. It's just whatever electrons it has, all by itself, that determines its charge, that determines its oxidation number. If the substance is involved in a molecule, if there is more than one element involved, then the sum of the oxidation numbers of those elements has to add up to whatever the overall charge is. So if the molecule, so this should say any neutral molecule. If the molecule is neutral, then the sum of the oxidation numbers have to add to 0. And we saw that here for the NH3. There's no overall charge. It's neutral overall. So the sum of the oxidation numbers for the 3 hydrogens and the nitrogen have to add up to 0. I've got a -3 and a +3. Add those together, I get 0. Right? So that's a rule. That's how oxidation numbers work. If I had an ion that had an overall charge, then the sum of the oxidation numbers would have to add up to whatever that charge is. And then there are a list of rules that allow you to, step by step, start assigning charges to different elements. But these rules are based on what we already talked about. They're based on the idea that when 2 atoms are sharing electrons, if one's more electronegative, we're going to assign all of the shared electrons to the more electronegative atom. We're going to split up the bond, assign all the electrons to the more electronegative atom. If you do that, you will get these rules. You will get this trend of oxidation numbers formed as a result of that process. So these are on the formula sheet. You don't have to memorize them. But we can apply them as well as the other method. So we can apply both methods here. So I might give you a compound and say, what's the oxidation number for the carbon atom in that compound? Or what's the oxidation number for the oxygen or the hydrogen? Right, so let's say I ask you about the carbon specifically. So the first method we talked about would be to draw that structure and divide up the electrons. So this slide is nice because it also illustrates the difference between what you do when you're calculating formal charge versus what you do when you're calculating oxidation numbers. Right, so if you recall, formal charge, to assign the electrons around an atom to calculate its formal charge, we always took half of the shared electrons. Right? The formal charge is equal to the number of valence electrons that would normally have to be neutral minus all of the lone pair electrons plus half of the shared. And so what we're doing there is any shared electrons between two atoms, only half of those shared electrons actually are assigned to the atom itself. Right? So for the formal charge for carbon was 4 minus 0 lone pair electrons and half of the 8 shared electrons, so that would be 0. Right? So that's what we used to judge whether the carbon was stable. When we drew a Lewis structure, we calculated its formal charge that way. Oxidation number is very similar, except instead of splitting up the electrons and always splitting shared electrons evenly, we use the electronegativities to split the electrons unevenly between atoms with different electronegativity. So because oxygen 3.5 is more electronegative than carbon, and carbon is more electronegative than hydrogen, we can use those differences to split up the electrons. So if I want the formal charge for carbon, I split all of the bonds evenly, and I assign only half of the shared electrons to the atom to calculate its formal charge. If I'm calculating the oxidation number, then for a bond, I don't split it up evenly. I don't assign half of the shared electrons. I either assign, well, I do that if the atoms have the same electronegativity. If they have the same electronegativity, I split them evenly. I assign half the shared electrons, one to each. But if they have a different electronegativity, I don't split them up and I don't assign half of the shared electrons to each atom. I assign all the electrons shared to the more electronegative atom. So the carbon doesn't have the 2 electrons it's sharing with oxygen assigned to it. But it is more electronegative than hydrogen, so it has all the electrons it's sharing with hydrogen all to itself. So then, if I were to calculate its oxidation number, I would use the same formula, but the method of assigning electrons is different over here. So the formula would still be the valence electrons on carbon, it needs to be neutral, which is 4, minus, in this case, the 6 I've assigned to it, so its oxidation number is minus 2 in that molecule. Questions about that? So just to look at the other method, so what we found here was that the carbon's oxidation number was a minus 2. The other method, I would look at that list of rules and I would apply them from top to bottom. Right? They're in the order specifically because the top rules are priority over bottom rules if there's any conflict between what the rules are telling you to do. So for carbon, the first rule is in the molecule overall, if it's neutral and there's no overall formal charge, then the sum of the oxidation numbers for the hydrogen, carbon, and oxygen have to add up to 0. So if I have 1 carbon, 4 hydrogens, and 1 oxygen, whatever the oxidation numbers are, they have to add up to 0. And then I would go to my list of rules and start assigning. So there's no fluorine, I skip that. There's no metal, I skip that. The next thing is hydrogen. Hydrogen should usually have an oxidation number of +1. So I assign a +1 to each hydrogen. And since there are 4 of those, that gives me a 4+ total. Then I go back to the list of rules. The next thing is oxygen. Oxygen should have a -2. And there's only one, so that brings a -2 to the overall sum of the oxidation numbers. So if I add these together, I'm going to have a +2. I can't, though, because the sum of the oxidation numbers has to be 0 if the overall charge is 0. So what must the oxidation number be on the carbon for that rule to be in effect? It must be a -2, right? Which is what we already determined by the other method. But if the carbon is a -2, then when I add these numbers together, then I get 0. So by this method, I look at the formula, I start assigning oxidation numbers for the elements on that chart in order until I have only one atom left, or one element left that doesn't have a number. Then mathematically I look at what the sum of the oxidation numbers need to be based on the overall charge, and I figure out what this last element's oxidation number needs to be so that the sum of them all add up to whatever the overall charge is on the molecule. So that's the second method. So this is a tricky thing. Students have a little bit of trouble with this, so let's look at some more examples. So let's look at ClO3. We'll first use the first method. So if I were to draw a Lewis structure for this, so it's nice to have two methods, because if you don't feel confident in your ability to draw a Lewis structure, the first method might not work for you. You can use the rules on the formula sheet and use the second method. But if you feel real confident about your Lewis structure skills and you're more a visual person rather than mathematical, and you want to see the electrons being split up, then maybe the first method will be the one that you prefer. But if we use the first method here, drawing the Lewis structure, counting up the number of valence electrons to know how many you put in here. I put the chlorine in the center because it's less electronegative than oxygen. And when I add up all of the valence electrons, I get 26. So I start applying those to my molecule. So that so far is 24. So I got to put 2 more on the chlorine. So now I have a Lewis structure. I know that the overall charge is -1, so I'll use that in the second method. But in the first method, I don't really need to worry about that. I just need to look at the shared electrons, and instead of sharing them evenly, allow them to be pulled to the more electronegative atom. And oxygen is more electronegative than chlorine, so I will assign all the shared electrons. So maybe I'll make these in red. These were the ones that were shared in their bonds between the atoms. I'm going to assign those to the more electronegative atom. Then I'm going to just look at what the charge would be. So for each oxygen, it would normally need 6 to be neutral, but I had 8 assigned to it, so that's a -2. So each oxygen has a -2 oxidation number. Looking at the chlorine, normally needs 7 to be balanced. But in this case, I can only assign 2 to it. So that means the oxidation number of the chlorine is a +5. That's right. We got it right. That was good timing. Questions about that? Okay, so then let's look at the other method. So the other method is to focus on the formula. It's a little bit more mathematical. So you look at the rules, you go down the list of rules. In this case, I know that the total sum of the oxidation numbers is going to have to be equal to -1 because the overall charge is -1. Then as I go down the list, I don't see anything about chlorine until later on. At first I see something about oxygen, which says oxygen's oxidation number should be -2, which is what we calculated by the other method anyway. Since I have 3 of those, the sum of each of those oxygen's oxidation numbers will be -6. So what must be the oxidation number of the chlorine? If I'm going to add these together and have it add up to -1, it's going to have to be 5. 5 minus 6 equals -1. So the oxidation number of the chlorine, since I only have 1 of those, is going to be 5. Questions about that? Okay, so that one worked out for you. Here's another example, H2SO4. By the first method, I put the sulfur in the middle, connect my oxygens. I've got two hydrogens, and the sulfur really has as many bonds as it needs, so I'll put the hydrogens on the oxygens. Count up the valence electrons, 2 plus 6 plus 4 times 6 is going to be 32. So already I've used 2, 4, 6, 8, 10, 12, so I've got 20 left. I've got to put those in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. A little premature that time. We weren't done. So I've got a reasonable Lewis structure. I might recognize that there's resonance here. In this case, that's not really necessary because even if I think about the resonance and I start sharing... Whoa, that was weird. Try to hit... Huh. Okay, well, let's fix it. Let's take a second. Even if I think about the resonance and instead of having this last lone pair here, maybe I erase that and put it here. That is a reasonable resonance, but it's not going to affect the oxidation number because whether I'm sharing 2 electrons here in a single bond or 4 in a double bond, when I go to calculate the oxidation number, I'm still going to split all of the shared electrons unevenly. If they have different electronegativities, I'm going to push them all for the more electronegative atom anyway. So it doesn't matter whether I have a single bond or a double bond there if I'm calculating the oxidation number. So once I have my Lewis structure, then I want to split up the shared electrons toward whatever the more electronegative atom is. So between sulfur and oxygen is more electronegative. So I split all the shared electrons between those two to the oxygen. And between hydrogen and oxygen is more electronegative. So I'll put all those on the oxygen. Then I just calculate what the charges would be. So for the oxygen, each one has 8 electrons. So it's going to be 6 minus 8, negative 2. Each oxygen is going to have a negative 2. For the sulfur, it needs 6 to be neutral. It has 0 assigned to it. So it's going to be a plus 6 oxidation state. For each hydrogen, it needs 1, but has 0 assigned to it. So that's a plus 1. Questions about that? Okay, looking at the other method. Start with the formula. Start with the oxidation numbers we know. That means look at the table in the textbook or the rules on the formula sheet. That in order, the first one that comes there is fluorine, but there's no fluorine, so the next one down is oxygen, which means the oxygen should be a minus 2. So in this case, the overall structure is neutral, so the sum of the oxidation numbers will have to be equal to 0. And if each oxygen has a negative 2, and there are 4 of those, I get a negative 8. Okay? So on the exam, and this is always a confusion for students, when I ask for the oxidation number, I'm not asking for this number, the negative 8. I'm asking for the negative 2. The oxidation number is the property of an individual atom. So you have to be able to calculate the sum of those oxidation numbers to make sure that they're correct and they add up to what the overall charge is. But when I'm looking for oxidation number for an atom, I just want the number for just one of those atoms. Okay? So that's a negative 2 oxidation state for oxygen. Looking at that list of rules going down, the next thing tells me that hydrogen should be plus 1. And if I've got 2 hydrogens, that's going to add up to a total of plus 2. So then I know for the sulfur, when I add that together, I need a plus 6 so that the sum will add up to 0. And since I only have 1 sulfur, I divide by 1, and I get a plus 6 for the sulfur's oxidation state. Questions about that? Okay, so that was worked out. So the next one is trickier. This one is going to be hard for you to draw a Lewis structure for because manganese is not a nonmetal. In other words, it's a metal. However, its positioning on the periodic table is not very far to the left, and it's also not very far to the bottom. So what we know about metals is they have loosely held outer electrons. But the most loosely held ones are near the bottom left, right? Because if they have the ability to make a noble gas configuration by losing electrons, and they have lots of shielding, so their outer electrons are not held very tightly. But manganese is not down there, and there are other elements in this area, other metals, that can get involved in sharing electrons. So from the point of view of manganese, you'd say, well, why not share electrons? It has a fair amount of positive charge in its nucleus to attract electrons. It has space in the third energy level to share electrons. So the manganese could lose a couple of valence electrons, the 4s electrons, and become a positive charge. Or it could share electrons. It doesn't need to lose them because either way it's never going to make a noble gas configuration. So here's a metal that could be involved in sharing and it might not. But we didn't talk about drawing Lewis structures involving shared electrons between metals and nonmetals. So in this case, it's going to be hard to use method 1. We'll have to rely on method 2 because we didn't really get that depth into that depth for drawing Lewis structures for substances like these. But method 2 is reliable, and so we can apply it. So if we apply method 2 here, we've got this formula. So the first thing on the list of priorities tells me that if the overall charge is 0, that the sum of the oxidation numbers has to equal 0. The next thing tells me that if I have a metal in group 1A, its oxidation number will be +1, right? Because metals in 1A like to lose 1 electron and gain a +1 charge. That's its oxidation number. We're not going to have extra electrons assigned to a group 1A metal. It's not going to have those electrons. It's not going to be sharing them. So I recognize for potassium, its oxidation number should be a +1. And since I've got one of those, that's going to contribute +1 to the overall sum of the oxidation number. There's nothing in the list of rules about manganese. But oxygen is there. The next thing down tells me that oxygen's oxidation number should be a -2. And since I've got 4 of those, that adds up to a -8. So in this case, what should the oxidation number be for the manganese? It's going to have to be a +7. Since I have one of those, that 1 manganese is accounting for the entire +7 oxidation. Questions about that one? What's the oxidation number for manganese? In this molecule, it's +7. What if I just had one single manganese atom? What would be its oxidation number? 0, if it's neutral. What's the oxidation number for an individual manganese ion, maybe that has a +2 charge? +2, right? So just to remind you, it's complicated if you have a formula that involves lots of elements. You've got to use one of these two methods. But if you just have a single atom, whatever its charge is, that's its oxidation number. All right. Seems like a reasonable place to take a break. Let's take a little break here, and then we will pick up in about 10 minutes and finish. And then you guys have the rest of the time for lab. Okay, talk about some of these reactions a little bit more. So another term that they use in the textbook that I don't think is really that helpful is a displacement reaction, but probably not going to just ask you to define that. But if you ever see the word displacement reaction, what they're talking about is replacing one atom with another in a compound. So in this case, you can see that initially the copper and the chlorine are together, and that is an ionic bond. So the copper has a +2, the chlorine has a -1. There are 2 chlorines to keep the charge balanced. In the end, the zinc basically comes in, bumps out the copper, and replaces it, and now it's with the chlorine instead. So the reason for that is because of the difference in charges. So the chlorine is not changing its charge. It's staying negative on both sides, but the reaction between the zinc having 2 electrons and the copper having a 2 plus and being able to accept those 2 electrons, that makes the copper neutral. So it no longer attracts to the negatively charged chlorine. And the zinc loses those 2 electrons and becomes positively charged. So this is the redox process. So really the nitty-gritty of what's happening here is the exchange of electrons between the copper and zinc, the same type of reaction we already talked about. The role played by the chlorine is really just a spectator. So it could be considered a spectator ion. It's just there to keep the charge balanced, right? Because if I want to deal with or get a solution of copper ions, I can't do that. You can't have a sample where every unit in that sample has a positive charge or a negative charge. Because as we talked about earlier this semester when we first started talking about ions, if every unit had a positive charge, it would just build up. Right? And you would have billions and billions of tiny amounts of positive charge. It would build up to a huge quantity of charge. It would be like a lightning bolt in your beaker. So you're never going to be able to get that situation. So if you want to introduce this copper as an agent that's going to accept electrons from the zinc, it has to start with an overall balanced charge. So you need a spectator ion, you need the chloride to do that. And since that also falls under the category of a displacement reaction, they kind of present it that way in the textbook. But I'm more interested in that you understand the redox part of it. The actual reaction part. The part that the chloride is involved in is really not that significant. It's just there to keep the overall charge balanced. So it's the oxidation of the zinc and the reduction of the copper that we're more interested in. So we can also, if you want, we can look at the oxidation numbers here as well. So the zinc has a neutral atom, oxidation number 0. The copper has a neutral atom, oxidation number 0. The chloride is going to have a -1 charge, so that's its oxidation number. The sum of the 2 chlorines is going to be a -2, and the copper's charge is going to be a +2. So when the particles are charged, the oxidation numbers are straightforward. Whether I've got an individual atom by itself, whatever its charge is, that's its oxidation number. If I've got an ionic compound between a metal and a nonmetal and they're charged, whatever their charges are, that's going to be their oxidation number. Right? So it's a lot more straightforward in that situation. And I can still use the oxidation numbers, so the chlorine's oxidation is not changing. It's not undergoing oxidation or reduction. It's just a spectator. But the zinc is. The zinc's going from 0 to +2, that's an oxidation. And the copper's going from +2 to 0, that's a reduction. So it's still useful to have the oxidation numbers to tell what's happening in the reaction. So what we find then is if we looked at the copper and the zinc, and we saw that the copper, if we put these two together, the copper plus ion has the ability to attract electrons away from the zinc. And that will neutralize the charge of the copper and create a zinc +2. If I were to reverse that and start with the electrons on the copper and have a zinc +2 that can pull the electrons potentially from the copper, I find nothing happens, no reaction. So that tells me something about the relative strengths of copper versus zinc to attract electrons. And I can do that competition experiment with all the metals on the periodic table if I want, and create a table of their relative abilities to attract electrons. That's called an activity series. So this is just a short section of that table, a few examples from the table. There are lots of metals in the table, including all the metals is much larger. But generally, the way this table works is at the top of the table, those are the elements that have the more loosely held electrons. Those are the elements that more readily undergo oxidation, the elements that are not good at holding their electrons in, so the electrons get pulled away when they're in competition. When those electrons are being competed over between two different metals that have the ability to possibly attract it. So if I compete zinc and iron, zinc will lose the electrons, iron will gain them. And when I look near to the bottom of the table, what I find are elements that are precious, like gold and silver and platinum, mercury. Those are the elements that attract their electrons more effectively. So that's what makes gold and platinum precious. It's not because they're rare metals. There are lots of metals on the periodic table that are way more rare than gold. What makes gold precious is the fact that it doesn't easily oxidize. Right? You want to make jewelry, you want it to look beautiful, you don't want it to rust, you don't want it to tarnish, you don't want it to be corroded. Right? So you want the metal atoms to hold their electrons, because it's the neutral metal atoms that have that shine and that luster that is appealing. So when a metal atom holds its electrons in, and you get that neutral metal material, that is, that's what we consider to be nice for jewelry, and it also has a lot of industrial applications. If you have a metal that can hold its electrons, then it's not going to rust over time. It might be good to put that into a material that might be exposed to the elements, and then you don't have to worry about it corroding or oxidizing. So the elements, so we can use this table to rank them, and if we look at the table, we can see which elements hold their electrons most effectively compared to other elements. And those elements have the ability to grab electrons from other things that are higher up on the table. Elements higher up on the table, if you start with them having electrons, they don't hold them tightly. Right? So this also allows us to think about how to design a battery. Right? The best battery would be one where on one side of the battery, I have my barrier down the middle of the battery, but on one side, I've got a substance that really has very loosely held electrons. And on the other side, I have a substance that can really attract those electrons. The bigger the difference between the two substances and their ability to attract electrons, the more potential there is for that battery to have a higher voltage. So that's also valuable in that respect. And it's also valuable for predicting reactions. So if maybe I have, for some reason, I have cobalt, and I want to have my cobalt metal, and in whatever industrial application, it's going to be in the presence of barium ion. I want to know, is this cobalt going to be able to stay, or is it going to react? Is it going to be corroded away by the barium? So I would find the cobalt and the barium on my table, and I would compare where they are. And so in this case, what this table is telling me is that the barium has a better or stronger tendency to be oxidized than the cobalt. So if I start with the barium joined with the nonmetal, that means it must be the one with the charge to balance out the charge of the spectator ion, the iodide. And the cobalt has no charge. Will they react? Will I see a reaction? Will I see a redox reaction? In this case, no, because the ones at the top of the table are the ones that have more loosely held electrons. They don't attract electrons as well. So if I start with that one, the barium, which is closer to the top, already not having the electrons, it's not going to pick any electrons up. It's just going to sit there because it doesn't attract the electrons as strongly. It's the ones at the bottom of the table that attract electrons better. And so if the cobalt is already below the barium, that means it attracts electrons better than barium. And if it's the one that already has its electrons intact, it's not going to lose them. So there's not going to be any reaction here. So I would predict, if I ask you on an exam, this one's going to give no reaction. I'm not forming any products there. What about the second one? Here I've got tin versus copper. The tin is starting off as a neutral metal. So I'm never going to see the metal usually become negative. That doesn't happen very often. So all the metals have relatively loosely held outer electrons. They're not picking up more than they need to be neutral. But if the metal starts neutral, it could lose some electrons because all metals have somewhat loosely held outer electrons. But their metals are different from one another. So this time I've got a competition between the copper 2+ and the tin. So are they going to react? Yes, they will, because copper is below tin. So on the table of my activity series, that tells me that copper attracts electrons more than tin. And so if the tin has the electrons and the copper does not, then the copper will attract those electrons. It will become a neutral copper, and the tin will gain a charge, and that will cause it to attract to the spectator bromide ions. So I can predict not only that there will be an exchange of electrons, but also what the products will be after that exchange. Silver, if I have silver jewelry and I expose it to salt, will it react? No, it shouldn't react. And I know that because sodium, if it starts with a positive, is much better at losing electrons than the silver, which is closer to the bottom of the table. So the sodium has more loosely held electrons than the silver. So if they did react, you know, if the silver is a 1 electron, if it did go to the sodium for a second, since the silver attracts the electrons better than sodium, it's just going to grab that electron right back. And so I won't have any reaction here, since the atom that naturally attracts electrons more is already starting with the electrons. The other atom's not going to be able to pick the electrons away from it. So you should be able to predict the outcome of reactions based on the activity series. This is the table from your textbook that lists more of the elements from the periodic table and how they react. And you can see that what we have in common is that at the top of the periodic table, I guess I'll stop here, these are all group 1A and 2A metals, right? Why are the elements at the top of the periodic table having such loosely held outer electrons? Yeah, because if they lose their electrons, they make a noble gas configuration. So they're the ones with the most loosely held outer electrons. So that's one way you can remember. If you have trouble, you know, you have this table, it lists all these metals. If you have trouble remembering, was it the metals at the top that have loosely electrons, or the ones at the bottom that have more loosely held outer electrons? Well, just look at what the identity of these elements are. It's the ones at the top that are all in group 1A and 2A. And we already know that those ones don't hold their electrons, because if they lose them, they make a noble gas configuration. So they're very easy to pull electrons off of these neutral atoms and make them charged. And they rust. Rust is termed specifically for when iron loses electrons, but when any other metal loses electrons, it's corroding, right? So you can't have a chunk of magnesium metal or calcium metal just sitting around as a neutral atom, because the oxygen in the air and water and other things can grab the electrons because they're so loosely held. But if you have platinum or gold, so these elements hold their electrons much more strongly. So you can have those exposed to air. Nothing's going to happen to them for a long time. So this is, we mentioned this a little bit, just a couple more examples here. In terms of balancing reactions, we know that if we're going to do calculations involving a reaction, we need to balance the reaction. That's the very first thing we always have to do, right? Because if we don't have the correct coefficients here, the correct numbers here in the balanced reaction, I can't answer questions like, how much copper do I need to react all my, or this is chromium and nickel. How much chromium do I need to react all my nickel? If I wanted to do a reaction between chromium and chromium metal and nickel ions, I need to know how much of that to put in if I'm going to set that reaction up. So if I'm working with specific quantities, I need a balanced reaction first. So if you just look at this reaction, does it look balanced? It looks balanced. From the rules we've talked about for balancing, I've got one chromium on both sides, I've got one nickel on both sides, it looks fine. But it's not balanced. So when you're balancing reactions, not only do you have to not create or destroy elements from existence, because that's impossible, but you also have to not create or destroy electrons from existence, because that's also impossible. So what we have to recognize here is not only does the number of each element have to be balanced, but the number of electrons transferred has to be balanced. I'm not going to transfer 3 electrons and then only accept 2. The other electron can't just disappear. Or I'm not going to transfer 2 electrons and then somehow create a new electron from nothing and somehow accept 3 when I only started with 2. That can't work. That doesn't happen. So when you're balancing redox reactions, one thing you want to think about is writing the individual half reactions. And so break down the overall reaction, write the oxidation part. What's happening for one of my elements? So maybe I look at the chromium first. The chromium starts with no charge, becomes a +3. What has to happen with the number of electrons for that to take place? Well, it has to lose 3 electrons, right? To go from 0 to +3, it's giving away 3 electrons. That happens to be the most common form for chromium. So chromium's ability to attract electrons is not very good. So when chromium forms a positive charge, it usually loses 2 valence electrons plus 1 more. It just doesn't have the ability to attract that 3rd electron in very well. Nickel, however, has more of a tendency to only lose 2 electrons and gain a +2 charge. So if you buy nickel ions, usually they're going to come in the form of a +2. And so if nickel is going to pick up electrons, it can't really pick up 3. Like the chromium can give away 3, but the nickel can't pick up 3. I mean, chemically, what would it do? It would put 2 in the valence level, and then 1 more electron in there. It's going to give it a negative charge. Most metals don't have the ability to attract electrons well enough to take on a negative charge. So the nickel really can only pick up 2. And also I know that because if it's going from a +2 to a neutral, that means it has to pick up 2 electrons to do so. So when I break down the half reactions, I can tell by the charges that are there how many electrons are given away by the one side of the reaction and how many are accepted by the other substance of the reaction. Those numbers of electrons have to be equal or the reaction is not balanced yet. And at this point, they're not equal, right? I can't create 3 electrons and then only accept 2. So what I need to do is to add coefficients. When I'm balancing a reaction, I add coefficients until everything's balanced. So if I've got too many electrons on this side that are being given away, I need to have more accepted. So I need to multiply all the so I still need to keep the nickels balanced. And I can't just say, well, I'm going to accept 3 electrons because I need it to be balanced, because the nickel really can't accept 3 electrons. It can only accept 2. So I can't really change change the ratios I have there. I can only add coefficients to change all of these at the same time without changing their the way they are relative to one another. So if I need to get equal number of electrons given away as I have received, the lowest common multiple of those will be 6. So I need to multiply everything here by 2. 2 times 3 is going to be 6. And I need to multiply everything here by 3. 3 times 2 is 6. Now, 3 times 2 is 6. Now I have 6 electrons given away and 6 accepted. Now they're equal. So now that they're equal, I can think about them canceling. They're on opposite sides of the arrow, so they cancel out. And then I write the sum of these 2 reactions. Add everything on the left. Add everything on the right. Should be a 3. Now my reaction is balanced because I have both equal numbers of each element on both sides and equal numbers of electrons on both sides. So you should be able to do that as well. Any questions about that? So we talked about displacement reactions. Another type of reaction is combination reaction. This is pretty straightforward. Here we're just combining 2 different substances and we're making 1. Right, so a lot of these combination reactions are also redox reactions. Some of them are not. Some of them are. How do I know if it's a redox reaction? If I want to be sure, I calculate the oxidation numbers and see if they're changing. All right, so let's look at this one. We already did the oxidation numbers for this in an earlier example by the first method. And we saw what the oxidation numbers were, and then we used the second method to confirm that. So we found that the nitrogen's oxidation number was 0, hydrogen 0. Here the nitrogen was a -3, and here each hydrogen was a +1. Right? So we got the oxidation numbers already. So is it a redox reaction? Yes. I can tell that because for each element, one at a time, I look at the nitrogen. Its oxidation number is changing. It's decreasing. That's a reduction. Then I look at the hydrogen. Its oxidation number is also changing. It's increasing. That's an oxidation. So if I know the oxidation numbers, I can tell whether it's a redox reaction or when the reaction takes place. What if I had this reaction here? Is that a redox reaction? Well, if I can recognize that it's an acid-base reaction, I know it's not a redox reaction. But I could confirm that by calculating the oxidation numbers for this reaction and show that they're not changing. But I recognize it's an acid-base reaction. We talked about this last time because I have a base that's going to be able to accept an H+, an OH-, and an H that could be donated by the Cl. And so if the OH- picks up the H, they join together and form water. So if my base happens to be an OH-, I form water and a salt. But if I calculate the oxidation numbers here for each element using the rules, using either one of the two methods, I find that none of them are changing. The hydrogen is always +1, here, here, here. It's not changing. The chloride stays -1 in each side. The sodium is +1 on both sides, and the oxygen is a -2 on both sides. There's no change, so it's not a redox reaction. And you'll find in any acid-base reaction that the redox oxidation numbers will not be changing, so acid-base reactions are also not redox reactions. Here I have the opposite of a combination. I have a decomposition. So instead of combining two things to make one, I have one thing breaking down to make two. That's a fairly common type of reaction. So if I want to also know if the decomposition reaction also happens to be a redox reaction, I calculate the oxidation numbers. So if I look at the oxidation numbers, I see the sodium is going down from a +1 to a 0. That is a reduction. And the hydrogen is going up from a -1 to a 0. That is an oxidation. Well, I shouldn't be looking at that. Sorry, I should be looking at the oxidation number. Not necessarily this. So the red box, the way they do the red box, that's the sum of the oxidation numbers. The blue circle is the oxidation number itself. So I'm comparing how the oxidation number changes from the left to the right. Not all decomposition reactions will also be redox reactions, but many of them will be. And so what we're seeing as we go through these examples is that there are lots and lots of different redox reactions. A very common type of reaction, which is why they focus on so much in this course, in this section. Another type of reaction is the disproportionation. So in this context, the disproportionation reaction is one where one of my elements is oxidized and the same element, a different atom of the same element, is reduced, right? And so I can see that here if I look at the oxidation numbers. So if I look at this H2O2 molecule, some of you did this Lewis structure for the fourth lab experiment where we were making the models for the Lewis structures. Here, if I apply my method and break the bonds, the oxygen-oxygen bond is going to break evenly because they have the same electronegativity. But the oxygen-hydrogen bond is going to break so that all the electrons go to the oxygen. So that's what gives me my -1 oxidation state for oxygen. Normally oxygen forms a -2 in most situations, but here its oxidation number is -1 instead of -2 because I can only assign 7 electrons to each oxygen instead of 8. Right, so that's 6 minus 7 gives me a -1. And the hydrogen is still a +1 because it has no electrons around it. On the product side, though, if I look at the water, in the water molecule, when I apply this method, I break the bonds, put the electrons on the more electronegative atom. Now my oxygen is 6 minus 8. It's back to the -2. And the hydrogen is still a +1. In the O2, they're breaking evenly. So here I have 6 minus 6, or 0, so I get an oxidation number of 0. Right, because they have the same electronegativity. When I break it homolytically or evenly. So, which substance is being oxidized? It's the oxygen. The oxygen is going from a -1 to a 0. That's an increase in its oxidation number. Going from negative to 0 is an increase. That's an oxidation. Which element is being reduced? Also the oxygen. There's a reduction because one of the oxygen goes from -1 to -2. That's a decrease. It's going down. So that's a reduction. So the hydrogen isn't changing here. The hydrogen's oxidation number starts at +1 and ends with a +1. So a disproportionation reaction is one where it's the same element. Some of the atoms of that element are undergoing a reduction, and other atoms of the same element are undergoing oxidation. Combustion is also a redox reaction. This is a very important reaction for our society as long as we continue to power ourselves using fossil fuels. That means carbon. Carbon, hydrogen molecules. Methane is one of those. And so if I calculate all the oxidation numbers, I find that the carbon goes from a -4 to a +4. That's an oxidation. Increase in the oxidation number. The hydrogen is not changing. It's the oxygen that goes from 0 to -2. And so that's a decrease. That's a reduction. So both oxygens are being reduced, and the carbon is being oxidized. So when one element's reduced, there will always be one that's oxidized as well. You can't have one without the other.